Good afternoon. My name is Theresa Stack. I am an assistant professor at Montana Tech of the University of Montana, and this learning unit is going to cover case control studies, and it's part of the principles of epidemiology. By the end of this presentation, you should understand what a case control study is, the different types of selections that you use, whether you're selecting your cases or selecting your controls, and the importance of matching in a case control study, and how it's used more than intervention studies as well as cohort studies in the area of occupational epidemiology. Well, if I recall correctly, on April 17, 1991, at 6:37 p.m. Eastern Time, I ate 6 ounces of grilled salmon, farm-raised, 2/3 cup of rice, 1/2 cup of steamed broccoli, 1 cup of mixed salad greens, and 2 tablespoons of French dressing, a 12-ounce glass of unsweetened iced tea, and 3 scoops of tin roof ice cream for dessert. And this is one of the problems with case control studies, is that they tend to be retrospective, and people have to look back and be able to reinvent what happened at some point in time. And the way we're able to recall information has to do a lot with how we were exposed to it, whether you are a case or a control. But another example, a really good example of a case control study, is when we did the outbreak of the food poisoning. And we found that, I believe, I can't remember specifically, it was the ice cream that caused the outbreak. That is a really good example of a case control study, and used an attack rate to be able to calculate that. So there is a link here. You can look at it on at your own time. I'm sorry, I can't select the links from the current online recording software that we're using. Cohort studies have an intuitive logic to them, but they can be very problematic when one is investigating outcomes that only occur in small fractions of exposed and unexposed individuals. So a cohort is a group of people. An example of a cohort study would be taking all of you in the epidemiology class and following you for the next 10 years and seeing which percentage of you graduates, and then which percentage of you that graduates gets a salary increase. That would be an example of a prospective, looking forward cohort study in comparison to a case control study. The other issue with cohort studies is that they can be problematic when it's expensive or very difficult to obtain exposure information from the cohort. So in these situations where disease is fairly rare, or it's expensive, or it's hard to study people over a long period of time, it's very expensive to do cohort studies, case control designs offer an alternative that is much more efficient. The goal of a case control study is the same as that of a cohort study, to estimate the magnitude of the association between an exposure and an outcome. However, case control studies are very efficient in doing so. In a case control study, we begin with the outcome and look for features of people who share that outcome, and then we compare it to characteristics with subjects who do not have that particular outcome. Case control studies are best understood by starting with a point, which would be a source population, which represents a hypothetical study population. The source population is a population that gives rise to the cases included in the study. Some of the key concepts in a case control design is all people who would be in the study base, the base population would be all people who would be in the study if they developed the disease. The disease has a clear definition, and it's usually newly diagnosed by a specific type of medical test or procedure. Controls are random samples of those people without the disease in the same study base, so in the same population. Exposures are evaluated by interviewing the cases and the controls. And of course, in all of our study designs, we have confounders, and that would be what can confuse the results. And then we analyze the data and maybe take a look at it for certain types of biases. Are the biases typical in a normal population? Are they atypical? Are they different because of the population in which you are studying? And so if you wanted to read a really good case control study, there's one posted on the web page under the assignment section. So case control study, we start with our source population. That's everybody who's likely to develop the disease. And then we are able to identify through a clear means of medical evaluation who are your cases, who has the disease, who has lung cancer, versus who does not have the disease. So we have our source population, and that's everybody who's likely to develop the disease or who has the potential for developing the disease. Then we break them down, we divide them into our cases and controls. And finally, we break them down one more time, and this is usually how some either interviewing is done, whether that's somebody with a field notebook taking answers, or you get a survey in the mail and you write a survey, and we find out which cases were exposed to the risk factors and which ones weren't, versus what controls were exposed to the risk factors and which ones weren't. And then we use analytical methods, and it's just like calculating your attack rates. We calculate an odds ratio. And we try to see whether the exposure to that risk factor is indicative of people developing the disease, or whether the exposure to the risk factor has no determinant on people developing the disease, or whether the exposure to that risk factor is somehow protective, and so it protects people from developing the disease. So an example that we can use, an easy example, would be workers in Libby, Montana, who worked at the vermiculite mine. And we gathered those people together. We separated which people developed asbestosis or mesothelioma and which workers didn't. And then we further evaluated their exposure. So a potential risk factor might be smoking. We know that smoking increases the likelihood that somebody's going to develop mesothelioma if they're exposed to asbestos. And so we can evaluate that risk factor specifically, not only the exposure to asbestos, because all these people were exposed to asbestos, but the added risk factor would be smoking. So you can kind of see how we break the data out, and we'll set it up in a data table. So cases are selected based on their disease state. They have it. They're selected after developing, or after a clear definition is developed of what that disease state is. It should be representative of all cases. Where do we find these cases? From hospitals, clinics, disease registries, injury and illness databases. Usually newly diagnosed people is preferred within a specific time period. Now our cases are selected from the same study population, but they do not have the disease. And you can find them from, again, medical institutions. They work in the same environment, or it could be a geographical sample. You can look at all the residents in Madison County and see which, and that would be your study population. And then we find our cases for developing bladder cancer versus our controls, which do not have bladder cancer, and was there something that differed in their exposure to specific risk factors. So we choose our cases first, and then we try to match our controls by different types of factors. For some of the ones that are really common are age, weight, sex. We might match them by smoking so that both your cases and your controls do smoke, and therefore it's not confounding because we know that smoking confounds most of our outcomes. Selection can be problematic. You try to find more controls than your cases, and also you can have multiple control groups. So your exposure or your risk factor, it can be habits such as smoking, behaviors, or food. It can be events such as a nuclear fallout or a spike in CO levels of admissions. The exposure must have occurred before the disease developed. And this is what leads to recall bias. Does somebody who has a particular disease, are they likely to recall their exposures differently than somebody who doesn't? So an example of recall bias would be, how many pounds of beef did you eat last year? Or do you drink, how much and how often? So this might not be recall bias, but it could be reporting bias. Maybe you don't want to report how much do you actually drink. So some other confounders. Confounders are described as factors that distort or mask the true effects of the study. And they should be addressed in an attempt to have validity in your study, and that can be done through appropriate statistical techniques. So when you're going through and you're choosing a paper for which you would like to review and do a critical review of as your final paper, think about whether all the biases were accounted for. Did the researchers address them or leave them up to chance? So how we calculate our, so we have our cases, we have our controls, we measure which ones have risk factors versus which ones don't. You can do that in many different kinds of methods, but let's just use yes and no right now because it's really easy to kind of get a grip on it. I mean, other ways that you could measure risks or exposure would be like in high, medium, and low doses. Sorry, I didn't mean to say like there. So if cases have a lower odds ratio than controls, the risk factor may be protective. If cases have a higher odds ratio than the controls, the exposure may increase the risk of disease. If odds ratios are equal, then the exposure is not likely to cause disease development. So let's take a look at that. Okay, so again, this would be probably important for you to write down the information and how you calculate an odds ratio, but we have done something really similar before when we calculated an attack rate. So an odds ratio for this particular case, study would be the numerator is the cases and the denominator is the controls. So you have the number of exposed cases divided by the number of unexposed cases. So in this example, we would take 40 divided by 10. And then we place that answer over the number of exposed controls, those who are exposed to the risk factor, over the number of unexposed controls. So in this example, it would be 15 over 30. And then to calculate our odds ratio, we take 4, the number of exposed divided by unexposed for the cases. We divide that by the number of exposed divided by unexposed for the controls, and we come up with 9.3. So the odds of exposure for cases is 9.3 times that of controls, meaning that exposure, smoking, asbestos, H2S, carbon monoxide, not wearing a helmet when you're riding your bicycle, is associated with a 9 times greater chance of developing the disease. pretty straightforward in calculating your odds ratios. And this is just another way of doing it, to put it in a table and do your cross multiplication. I think that whichever way that you are able to do your calculations, certainly you can come up with your own ways. You don't have to do math the way I do math, is what I'm trying to say. We all have different methods. So the advantages, again, there's another video here for you to click on that link when you go through and look at the unrecorded audio portion, which is so much more interesting than the recorded audio portion. The advantages are it saves time and money because you almost always have your data somewhere. You do have to data mine and pull your data. It can be used for really rare diseases, which gives you a chance to evaluate small sample sizes, and can be used to generate a hypothesis for further studies, which would be your clinical studies or your intervention studies. You can look at multiple associations, so multiple risk factors within a disease. Some of the disadvantages: it's subject to recall and reporting bias, it's observational, and it works only for certain types of conditions. So here's an example of Reye's syndrome and previous aspirin use. And for those of you who have young children, you've, I'm sure, been told to never give them aspirin because it can cause problems with their liver. So Reye's syndrome is a potentially fatal syndrome that has numerous detrimental effects to the organs, especially the brain, liver, as well as causing lower than usual levels of blood sugar. The classic features are rash, vomiting, and liver damage. The exact cause is unknown, and while it has been associated with aspirin consumption by children with viral illnesses, it also occurs in the absence of aspirin use. So what if we did a clinical trial? We took all the children born in 2007. We gave some of them aspirin, we gave some of them a placebo, and we observed over a period of time to see which people developed Reye's syndrome. Can we ethically do that? Can we do a cohort study? Can we find a large group of children, all the children born in 2007, follow them for 5 to 15 years, and among those children who develop Reye's syndrome, go back and see whether they had taken aspirin or not? Boy, that would take a long period of time. So instead, let's take a look at a case control study. So Reye's syndrome is extremely rare, and we would need a really large population if we were going to do either an intervention or a cohort study. So this is, some of these numbers are true numbers that came from the 1982 study. He had 25 cases of Reye's syndrome with children with prior infections, viral illnesses, and 46 controls with the same type of illness, but who did not develop Reye's syndrome. So your cases had it, your controls didn't. Now we want to go back and take a look at our risk factor. Our risk factor being whether the children took aspirin or not. So the parents were asked about aspirin use for the treatment of these illnesses. In 96% of the cases who developed Reye's syndrome were treated with aspirin, and only 76% of the controls were treated with aspirin but did not develop Reye's syndrome. I'm going to give you a little bit of time to kind of digest those numbers there. So it looks like a greater proportion of Reye's syndrome cases had prior aspirin exposure when compared to people who did not develop Reye's syndrome but still had aspirin exposure. Okay, so some of our important characteristics with matching. We try to match our cases and our controls with age, height, weight, other risk factors that they may be exposed to. And if we don't do careful matching, then we are unlikely to be able to really ascertain whether the disease was caused by the risk factors or not. Let's say we're interested in a residential proximity to hazardous waste sites as a risk factor for leukemia. We've had this ongoing discussion here in Butte, Montana many times. If we have identified the neighborhood of cases for our, if we have identified the neighbors of cases for our controls, then we may not see many differences between the cases and controls in terms of the distance to the hazardous waste site. So in effect, we have guaranteed that the cases and the controls do not have different exposures. So here we'd like to have our cases closer to the hazardous waste site and our controls further away from the hazardous waste site, so that would be the difference in the exposure. So what I'm saying, and I hate saying what I'm saying in other words, but what I'm saying is if your controls and your cases are too well matched and the risk factor exposure doesn't differ, you may not be able to see a difference in the disease outcome. So the following is an example and I thought there was another example in there. That's why I paused, because I just took a look at this. The potential risk associated with spray painting in the automobile industry. In a case control analysis, cases are defined as all lung cancer deaths among automotive workers. Controls are identified as those deaths due to circulatory disease or accidents among the same worker population, thus ensuring a valid representation of the worker population under investigation. And in this particular study, the company had a really good history of paint sprayers, as well as looking at who had passed versus who had not passed. So what population is the one for which we would like to know the proportion of employees who worked as paint sprayers? Apart from chance, how might the control group selected not accurately characterize the proportion of exposed workers in the population?